Welcome to Complexity Made Simple, and my name is Paul Allen. And before we get into today's fantastic video newsletter, what I'd like to talk to you about is all the materials that you can purchase to help to support the channel. We've got these fantastic textbooks that range from the simple statistical process control for small batch production. We've got the 7 quality tools for world-class problem solving, which is essentially yellow belt material. Then we move on to design of experiments for 21st century engineers. Every engineer and scientist needs to be able to do design of experiments. And then finally, drink tea and read the paper. The most fantastic green belt handbook you can buy on the market today, full of practical tips and fantastic physics that'll help you become a world-class engineer and a world-class quality engineer. Of course, you can also click on the link to buy me a coffee and make a donation. That would be fantastic. But at the very least, click on subscribe, click on like the video, because it all helps to support the channel. Many thanks for your help, and now on to today's video. Welcome to the latest video. And in this video, what we're going to take a look at is the idea of statistics being practical, not mathematical. Okay, so for me, and this is the way I use stats. Stats is a practical thing, not a mathematical thing. So this relates to the fact that I'm constantly asked questions about rules, how should I get my R squared, p-value levels, all sorts of statistical questions. But for me, whenever I'm doing heavy statistical analysis, and this particular tale is going to relate to doing a design of experiment, a DOE. Everything about a DOE is a practical thing. It's not a statistical thing. It's not about the maths. It's about what I'm seeing in front of me. Can I use it to solve my problem? Can I use it to save money? You know, what can I use the knowledge that's in front of me for? And that isn't about hitting a mathematical rule. So I want to just give you some context as to where this video has come from. So somebody sent me a comment, and by all means, by the way, please click like, leave a comment. It always helps with the channel. The more likes we get, the more other people get to see this video. But somebody left a comment, and I ask anybody to do this. I will react. If you want to ask a question, I will often make a video for you. They'd done a DOE. Now, when you run a designed experiment, one of the things that you should do as part of the procedure is do center points. All right, so you're going to run center points. Now, what center points are all about, of course, it's typically about confirming the model. Okay, so just to kind of give you a little bit of DOE theory. So let's say we're testing 3 variables: time, temperature, and pressure. We're going to test at those 8 corners, and we're going to assume linearity. But how can I confirm linearity? Well, you confirm linearity by doing this. You do a center point right in the middle of the box. So in other words, you're going to put a setting in the middle of time, a setting in the middle of temperature, and a setting in the middle of pressure. Where does that drive you to? It drives you to the middle of the box. Now, some people do these center points as part of the experiment. Some people do them at the end of the original 8-point experiment. And there are videos. I will leave a link at the end of this video to what are the center points for in a DOE, so you'll be able to see my explanation more about your center points and how to use them. But anyway, somebody had done their DOE and they'd run the center points and they got center point results that look like this. They got 13, 15, 25, 28 and 30. That's what they got. And they said, is this wrong? Was that, I think, the question. They said my lack of fit, so they'd been statistical. They were saying my lack of fit is okay, but is this wrong? I need to make a presentation in a few days. Now then, the first thing to say is, this is a practical thing, and without knowing the practical information to do with this experiment, I really can't answer this question, because this is all about, can I still use the model? Can I not use the model? So let's talk about the practical side of this. So is this wrong? You've obviously got this noise going all the way from 13 to 30. Now the question would be, what do you want to use the model for? What do you want to use the model for? What are you trying to hit? What's the tolerance that you've got? So the first thing to say, just showing you the way numbers can go good on you or they can go bad on you. I'll show you R squared, how to get a good R squared, how to get a bad R squared. It's dead easy to do. When you do an experiment on a process, you choose. So let's say this is temperature. You choose where you're going to do the test. So you can choose any temperature levels that you want to test. But let's say I choose 28 and 30 degrees centigrade. That's as wide as I go. Now the trouble with 28 to 30 degrees centigrade is that, of course, 2 degree shift isn't going to create much of a signal. Okay, so if you then get noise, like we've got here, got a lot of noise for the same setting. So we've collected 5 data points, all set to the midpoints here. If you get that kind of noise now, like that, and you don't shift the result very much. So let's say you've put a tiny little signal in like that. So if you look, the signal, look, is that big. That's the rise that you've created by going from 28 to 30 degrees. But the noise is massive. Now remember what an R squared value is. It is effectively a signal to noise ratio, because the more signal you get, the stronger the R squared, even if the noise remains the same. So it is a signal to noise ratio. So when you work out R squared here for this is probably going to be very poor. I don't know, I'm going to say 20%. But I could have artificially made my R squared brilliant simply by doing this. Look, I do the same trial, but I don't test 28 and 30. I go 10 to 40. I get the noise, but I get a much bigger signal. Now my signal is this big compared to my noise being that big. It's just a ratio, signal to noise. Now I've turned the whole thing around. Now I'm going to get an R squared of about 0.7. Now did the process get better? Well, it didn't. This was just purely, where did I do the test? Okay, where did I do the test? So I might still have this amount of noise here, but my noise here, look, is 27 units. My signal could be 100 units. So my signal now is 3 times bigger than my noise. R squared looks much better when that happens. And that's what's happened. So then somebody says, oh, well, you've hit a good R squared. Everything's right with the world. What has that got to do with anything? You see, what is it I'm trying to hit? Because if I'm trying to hit a target, you know, so here, look, if I set the thing to 29 degrees, and therefore it gets me to hit a target over this side. But my target has a requirement of being plus or minus, let's say, 4 units. So I've got a tolerance that looks like that. But I've got noise that looks like that. So even down here, I've driven my R squared up, but my tolerance, look, is still much smaller than my noise. So is it any use to me to be able to hit a target? You know, if I hit that target, will it remove my defect rate? No. The problem's with your noise. It isn't with your signal. So the R squared doesn't matter. It's a practical thing. And to kind of drive this home a little bit further with R squared, I've seen people get an R squared of just 0.3 but solve their problem because all they wanted to do in their system, so they got data, a fair amount of scatter in the model like this. So you've got the regression line and lots of scattered data around it. And they'd got an R squared of 0.3 because of this. But actually, all they wanted to do was push the process to this region. Now, the model was perfectly capable of doing that. So this area was good results. The model was perfectly capable of pushing the results to the good zone. So the R squared of 0.3 didn't matter. So in answer to your question, the person that's asked me this question, is this a bad thing? I don't know whether it's a bad thing because it relates to what you're trying to hit. If your tolerances can stand this, what is it, 17-point swing here. If your tolerances can stand a 17-point swing, everything's right with the world. It's not going to be a problem. If your tolerances are plus or minus 2, that's a disaster, and you should have removed the noise before you did the DOE. Very important, by the way. Get the process under control before you even do an experiment. But this is a practical response. You know, do I look at these? Of course I do. Does a good R squared make me feel good? Does it make me feel like I've done a good experiment? When I look at my repeats in my tests, is it nice to see values that are very close to one another? Yes, absolutely it is. You know, so when you see a set of results, do you want to see them all in the same zone? Yeah, that's a sign that you got the process under control. Everything was repetitious. It's a great sign for your experiment. But I look at these numbers. I'm not really looking at this. And it's exactly the same with p-values. When you get a good p-value, so often, of course, the p-value we're trying to beat is 0.05. So if I can get the signal to have a p-value related to it as below 0.05, that's a significant term in my model. And we use the term significant, but we mean that from a statistical point of view. We don't mean it from a practical point of view. You can have a p of 0.05, but if it's not useful to you, if the signal created won't help you to solve the problem, this p-value is not going to help you. You need the signal that you created to be practically useful. And that's the difference. Statistics has always got the two sides. Do we have statistical significance? Do we have statistical strength in the model? Yes and yes. Don't get me wrong. Is that a good thing to tick? It's always a good thing to tick. Does that mean this thing will solve your problem? No. You might have a more tricky problem to face than the model that you created. But you could also have really sloppy R squared and solve your problem. It depends on the physics and the problem ahead of you. It depends on the tolerance. So statistics to me is a practical thing. I'm an engineer trying to solve a problem. Do I care whether I get a good R squared? No. What I care about is that I solve the problem on my process. And R squareds are helpful, but they're not really the answer. So the person that asked the question, is this a problem? I don't like this because it's a sign that we haven't got control of the process, but I don't know what you're trying to do. So maybe that's okay. Maybe that's too much. If you want to send me another comment, because I will send this video to you, please by all means do. But really, use the practical, use your common sense. DOEs deliver knowledge. They don't deliver the answer. You got to be thinking straight and you use the knowledge. And if you use the knowledge properly, guess what you're going to do with the DOE? You are going to make more money.